All right, guys, last class we talked about finding areas using integrals, and today we're going to extend to being able to find volumes. And, you know, the big idea here is, remember that when we were doing areas, we started with Riemann sums, and we said the way we could find areas is by making an infinite number of very little rectangles, you know, and that will cover the area, right? So like if you make a bunch of infinitely thin rectangles, and we do the limit of those rectangles, we can find exactly how much area that was, and that was an integral. Well, it turns out that if you know the area along the way of a 3D figure, for instance, if you can calculate the areas of all the little shapes, you can actually make a volume, right? Just like a bunch of rectangles, a bunch of lines can add up to be an area. A bunch of 2D areas with infinitely thin width can add up to be a volume in the limit. And so this will also be an integral. If we add up a bunch of areas, it will give us a volume. So hopefully we can see that these are like super, super thin areas and like infinitely thin volumes. And so just like we used infinitely thin rectangles to make up area, we can use infinitely thin volumes to make up, infinitely thin areas to make up volumes. So here is the calculus. If you have cross sections, and a cross section, of course, is if you take a 3D figure and you, oops, that didn't work. Man, I was hoping I'd be able to show you that. You can cut it. So if you cut something, the cross section is the shape it makes when you cut through it. So like, for instance, the cross section of this 3D figure is a semicircle. Like if you were to cut it, you know, the shape you would end up with is a semicircle. The 3D figure here, if you were to cut it, is a square. That's the cross section of this 3D figure. These look like rectangles. So a cross section is when you cut through a 3D figure, what two-dimensional shape does it make? And if you have a volume and you know the areas at every point x perpendicular to the x-axis, the volume is going to be the integral from a to b. So from the beginning of the place in the x-axis where you're starting till the end of the x-axis of the areas. And this just says, look, you add up all these areas and it will give you the volume. And sometimes they will actually like tell you a formula, like in these problems on the AP exam, and honestly in real life. Like there are plenty of times where we know the areas along the way because we can measure them. But sometimes we can't. So if we know the areas, what we can do is we can just like literally do the integral of the area. So if they ever say like, hey, the area at each x is some function, then you can just do the integral of the area and that gets you the volume. More commonly, we have ways to figure out the area of each cross section and calculate it using some geometry. And we'll see that right now. So here's an example. Find the volume of a solid. A solid is a 3D figure. A solid is a 3D shape whose base, so the base of a 3D shape is like, you know, what's on the ground that's not sticking out. This is the base, okay? Whose base is the area enclosed, okay, enclosed by, so it's gonna talk about an area, enclosed by the line y equals, I'm gonna draw it over here, y equals negative x plus 6, so it's got a y-intercept of 6 and a slope of -1, so down by 1, over by 1, whatever. So it'll have, this will be its x-intercept. I'll just draw those 2 points. So y equals negative x plus 6, the y-axis, and the x-axis. Okay, so this is the base of the solid. And so there's some solid three-dimensional figure that's sticking up out of the page. I don't yet know exactly what it's going to look like, but I know it's sticking up out of the page because this is the base, is this area, the base of a solid, the base of a 3D shape. The cross sections perpendicular to the x-axis, so here's the x-axis, right? And if we do cross sections, that means we cut it perpendicular to the x-axis. If we were to like take my hand and slice it, this is what it would look like, a slice like this. If we slice through this 3D figure, it says the cross sections form squares. And what that tells me is that I know this is the base, and since the cross-section is a square, the height of this has to be the same. Whatever is sticking up has to be the same height as whatever the length is of the base. So we can see the base, if I cut it right here, okay, would have a height of this, because that's the cross-section of the base, and the height forms a square when we cut it. Now, these squares are not all the same width. Like, if we go to the end of this, now the cross-section, like if I cut it right here, if I cut it right, oh man, you guys, this is hard to, let me see if I can get a paper and see if this will work for you. We would normally do this with like Post-it notes, and it would make it really easy to see. If I cut it like right here, you guys can see that the actual shape that's cut out in the two-dimensional part of the cross-section is going to make a really tiny square. So this will be a really little square here. And over here, this will be the biggest square. The squares are actually changing size along the way. And it kind of looks like this. Like, you guys can see how this has little squares. This has little squares at the beginning, right? Sticking up. And then bigger and bigger and bigger squares. That's kind of what's going on here. There's like some big squares at the beginning, and then littler and littler and littler squares. And this is forming a 3D figure, and I hope you can see it kind of like almost goes down and makes a pyramid where this is the point of the pyramid. Like that's the shape it's making. Anyway, what we're looking for is, can we find the area at each x value? Are we able to find the area at each x value? And so what I want to do is I want to pick just a random location x. I'm going to call this x, okay? And I want to see, can I find the area at that x? And so I know it's going to make a square. And so the area of a square is the length squared, because they'll have this, it'll be this length times this height, but they'll be the same because it's a square, so it's just length squared. So the question is, what is this length at every x? I know it has a y-intercept of 6, and so when x equals 0, the length is 6. When x equals 1, the length will be 5 because the slope is -1. When x equals 2, the length will be 4. When x equals 3, the length will be 3. Until when x equals 5, the length will be 1. And when x equals 6, the length will be 0. So we can see that these squares will have different lengths along the way. I hope we see that. That's what I was talking about earlier. And it's actually based on what x you're at. And we can tell what the length is going to be based on whatever the height of this line is. And that's literally what this formula says. This formula tells you what the y value is at each x. When x is 0, so y of 0 equals 6, because -0 plus 6 is 6. The y value at 2, when x is 2, -2 plus 6 will be 4. The y value at 5, when x is 5, the y value will be 1, because -5 plus 6 is 1. This is a formula for the height of these rectangles. And so the area at each x will be the length squared, and the length is -x plus 6 times itself, -x plus 6 squared. So what is the volume then? The volume is the integral of this area. So the integral of -x plus 6 squared, this is the area, taken from the beginning till the end, from when x is 0 to when x is 6. Now, I want to let you guys do this integral on your own. And hopefully, we know that this is it looks like a chain rule thing. It's something squared. And so the antiderivative is going to be something cubed divided by 3. And then we also need to say, like, u is -x plus 6. And so the derivative of that inside function is -1. So we need to divide by -1. So it's going to be -1/3 -x plus 6 cubed. So I did the antiderivative by undoing the chain rule. That's u substitution there, and raising the power by 1 and dividing by 3. There's a couple ways you could have done that. And going from 0 to 6. So when I plug in 6, I get -1/3 of 0 cubed minus -1/3. That's going to end up becoming a plus, right? So we've got minus when x is 0. So minus -1/3 of 0 plus 6 cubed. So negative is plus, so it's 1/3. This is 0. 6 cubed, 6 times 6 times 6 is 216, but it's actually easier to do. So 6 times 6 times 6, a third of one of these 6's is just 2. So 6 times 6 is 36, 2 times 36 is 72. So 72 is the volume of this 3D shape. And if we had units, guys, this volume would be in like units cubed. So if this was like measured in inches, this would be inches cubed. Volumes are always in units cubed. Although that doesn't really come up on the AP exam very much, the units here. Okay, what if we had this same base, but now the cross sections were isosceles right triangles with a base in the xy plane? So again, okay, so let's look at what we got here. We've got this line, y equals negative x plus 6. And this is still going to be a base, but now what's sticking up are right triangles with a base here. So you've got like triangles, right triangles have a right angle, and they're sticking up out of the page. So, you know, it looks kind of like this, where there's like small, and again, because they are isosceles right triangles, that means this length and this length are the same. The length that is like forming the base of the triangle and the height of the triangle have to be the same as each other because they're isosceles triangles. These triangles are different sizes because, you know, oh man, these didn't have very equal. These are supposed to have equal sides because they're isosceles. So these are right triangles sticking up out of the page, you know, looking like this. So that's a little bit better. Again, they're big triangles at the beginning, they're little triangles at the end. We need to come up with a formula for the area of these triangles at each x. So let's say I'm at a given x value. What would be the area of this triangle? What is the area at each x value? And hopefully you can see that the way we find the area of a triangle is 1/2 the base times the height. And in this case, the base and the height are the same as each other. So it's 1/2 the base squared, and that's because they were isosceles triangles. And so the question just becomes, what is the base? Well, this is 1/2. This height is just this y value, like whatever the y, this is y equals 0, and this height will be y equals negative x plus 6, and so that's the height of this triangle. It's negative x plus 6 squared. So what is, if that's the area, what is the height, or what is the volume? Well, the volume is the integral from 0 to 6 of 1/2 negative x plus 6 squared, because this is the area. So it's the integral of the area at each x. Now, we can do a cool trick here, and instead of redoing this integral, I mean, we could redo this integral, but we can use our properties of integrals to pull out this 1/2 to the outside, and we already found this integral earlier. This integral was 72, right? Like this exact same integral, it's right here. And so it's 1/2 of 72. You can always pull a constant outside of the integrals, only if it's a constant, not a function. So this is going to be 36 because it's 1/2 of 72. Okay. Last one. What if sticking out of this same shape, so the same guy, y equals negative x plus 6. Now what if sticking up are semicircles perpendicular to the x-axis? So you slice it perpendicular to the x-axis, and what you find is that there are semicircles. So there are these little semicircles perpendicular to the x-axis. Okay? So this is a semicircle. I want you to, on your own, this will be a bunch of semicircles, is at a given x, find what would the area at that x be. And I hope we can see that the area of a semicircle is going to be 1/2 pi r squared. So the question is just, what's the radius of the semicircle? Well, the radius of a semicircle is from the center to the outside. So it's not this whole height, it's this part right here. So the radius is going to be from the center to here. Now that is 1/2 of this height. So the radius is 1/2 of this height. And again, this height is going to be at every x. We have a formula for what that height will be right here. So the radius is going to be 1/2 of negative x plus 6. That's the radius. And so the area will be 1/2 pi times 1/2 of negative x plus 6 squared. Notice that the 1/2 is part of the radius. It's also getting squared. And so there's a nice way the semicircle ones always come out to be like, okay, so you get 1/2 times 1/2, which is 1/4 because it's getting squared. And then 1/4, 1/4 times 1/2 is 1/8. And then you can multiply the pi on top if you want. So it becomes like pi over 8 times negative x plus 6 squared. And so like you end up with this constant in front of a semicircle that you can pull out again. So the volume is going to equal what? Well, it's going to be the integral from 0 to 6 again of pi over 8 times negative x plus 6 squared. And with semicircles, you're always able to pull out this constant of pi over 8. It'll always end up being pi over 8. So pi over 8 integral from 0 to 6 of negative x plus 6 squared, which is the same thing we had before. So it's whatever this came out, this volume was 72. So 72 times pi over 8. And we can do 72 divided by 8. This is 72 divided by 8 is 9. So this is 9 pi. So 9 pi is the volume of the solid if it's semicircles. So guys, we can have the same base, and depending on what shape is sticking up, we can have different volumes. Squares, you can have triangles, you can have semicircles, you can have rectangles, you can have trapezoids, and that's about it, guys. Like, there aren't a lot of shapes that you're expected to be able to calculate the area of. Triangles, rectangles, squares, semicircles could be sticking up. Yeah, there's trapezoids maybe. There's just not that many things. And so what you're doing is they're always going to tell you about what shape is, what they're often going to do is tell you about what shape is sticking up. And you have to find the area of that shape, and that will be the area at each x. And then we'll be able to use our volume formula that says it's the integral from the beginning to the end of whatever the area is. So here is another one. Let's look at this. The base of the solid, this is going to be a calculator one, guys. You're going to need a calculator for this. The base of a solid in the region, in the first quadrant, bounded by, so I'm going to draw a picture of this. The y-axis, the graph of y equals tangent inverse of x. I'm going to graph this. Y equals tangent inverse of x. So y equals tangent inverse of x. Let's graph it. Oh, and the vertical line, the horizontal line, y equals 3. I'm going to graph that too, y equals 3. And the horizontal line, x equals 1. So I'm going to make my window go from -1 to 2 and -5 to 5, just so I can see this a little bit better. I should have made it graph faster. So it looks something like this. So there's the graph of tangent inverse, and there's the graph of y equals 3, and we're talking about the first quadrant. So we're talking about this part right here. The area bounded by the line x equals 1, the y-axis, tangent inverse of x, and the line y equals 3. So I want you guys, actually, before we find the answer to this, I want you to find what is the area of this shape. I'm sure this came from a free response problem where they also asked for the area of this shape. What is the area of this region that's bounded here? And so I hope we realize that that's going to be the integral. So this is from last class, the integral from 0 to 1, because x goes from 0 to 1, of the top minus the bottom. This is y equals 3. So this is 3 minus arctangent of x dx. So you get, this area is 2.561. Okay, now I want to remind you, I really recommended we learn how to do this using the y variables. So math 9, we already put these into our functions here. Tangent inverse is y1 and 3 is y2. And so we can do top minus bottom by doing, remember we go to variables, y variables, we press enter, and we do y2 minus, in this case it's y2 minus y1 because y2 was on top. And that also comes out to be this. And you'll see this is going to get really useful in today's lesson. So I also want to show you If you accidentally get it backwards and you put y1 minus y2, because often it's y1 minus y2, it'll just come out the same thing but negative. And if it ever comes out negative, you should be like, oh, it's supposed to be a positive area or a positive volume. I'll just make it positive, and I know I need to switch it so that it was y2 minus y1. So if you're on the free response portion, you would just like change your work to be like, oh, it's the integral of y2 minus y1, not y1 minus y2. Okay, so that's that area. What about the volume? How is the volume going to work here? Well, they've told us the cross sections. It says each cross section perpendicular to the x-axis is a square. So we've got a square here. What is the area of that square at each x? What is the area of this square going to be? And hopefully you can see that it is this distance squared, because, you know, it's going to be the same sticking up as it is right here. And this distance from the top to the bottom is just the top minus the bottom. So 3 minus tangent inverse of x. But that's just this height. And so the square will have an area of this square. So the volume then is the integral from 0 to 1, because that's where this goes from 0 to 1, of 3 minus tangent inverse of x, all squared. Now guys, in a calculator, this is where we really want to do, like, check out how nice this becomes. So it's 0 to 1. You're going to open parentheses, and you're going to say y2 minus y1, close the parentheses, and square it. It's so often going to have y2 minus y1 squared in it. You want to get used to like just putting that in. You know, sometimes it'll have a pi over 8 or a 1/2 or whatever, but very often it's going to be y2 minus y1 squared, because like it's going to be, this will be the base, and most areas have a squared in it. And so this is the volume. So 6.612. All right, guys, I want you to try to do some parts of this one on your own. So you're going to need a calculator again. R is the shaded region. And I want you to start by finding the area of R. So what's the area of R? It's the region bounded by square root of x, e to the negative 3x, and the line x equals 1. So, use a calculator. You should start by graphing them. And hopefully when you do, you realize that the e to the negative 3x1 is the bottom one, and square root of x. You should know what these shapes look like. This is a square root function. Here's square root of x. Here's e to the negative something. It's exponential decay. So, and we're going from 0 to 1. I'm going to set my window to be negative 2 to 2, and I want to make it go faster because I get, oh no. What did I do with my window? I must have made it negative 2 to 2. Okay. So here we go. Here is that area, and we're going from here to here. Okay, so what do I need here? Well, I need to know, for my area, I need to know this intersection point. So press second, calc, intersect, number 5, enter, enter, enter. So the area is the integral from point 239 to 1. We don't have to find an intersection here because it tells us x equals 1 is the end, of the top one minus the bottom one. So square root of x minus e to the negative x. So the area, I'm going to press is math 9. It's the integral from point 239 to 1 of variables. It's, I believe I put y1, it was the square root of x1, but I'm not really sure. And honestly, even if I got it wrong, I know it'll just be the negative of this. So here's the area. It's 0.443. Round the 2 up. We always go to 3 decimal places, guys. So that's the area. Now, that would be if we were adding up a bunch of rectangles, right? But it says that the region R is the base of a solid. Remember, a solid is a 3D figure that's sticking out of this page. Like, I don't know what shape it is, but it's going to tell us right now. It says when they do cross sections perpendicular to the x-axis, so when it's a right angle to the x-axis, the thing that is sticking out of the page makes a rectangle. Okay, so now there are rectangles, and the height of the rectangle is 5 times the width. So we've got these like really tall rectangles sticking out. And it's going to be whatever the width is, whatever this is going to be 5 times as high, right? So what is the area of each of these rectangles at x? Well, the area of a rectangle is length times width. And the length of this rectangle is going to be square root of x minus e to the negative 3x, because that is the difference between these two heights. That's the length of the rectangle, right? So that's the length, and the width is going to be 5 times that amount. Whatever that amount is, the width is 5 times that amount. So whatever this is 5 times it. So 5 times that same thing, square root of x minus e to the negative 3x. This can be simplified a little bit. So the area is, I'm going to put the constant in front, and this is the exact same thing twice. So this is square root of x minus e to the negative 3x squared. So this is the area of the rectangle. So what's the volume? Well, the volume is the integral from, it's still from here to here, so from 0.239 to 1 of 5 times, I'm going to call this y1, and this y2, because that's what I put in my calculator. 5 times y1 minus y2 squared. So this is y1 minus y2 squared. By the way, you really want to put y1 equals square root of x. Like if this is the free response section and you want to use y1 and y2, you should label them like this. Sometimes they'll give you like f of x and g of x, and then you can just use f of x minus g of x. But if they don't have names, we should name them directly by writing it down. That way you get full credit for that. So this is it. So guys, this is going to look so similar to up above. Like finding the area and finding the volume are so similar. We need to have a 5 here, and then this was squared. And other than that, it's like the same thing, right? It's the integral. It's still the exact same place you would find the integral of the area from. Is for finding the volume. It's the same spot, so same limits on the integral. And we just need to change. It's not just going to be like the top minus the bottom. It's going to be whatever area the shape is that is made there. Okay. Oops. Let me actually calculate this. And there it is, 1.554. Go to 3 decimal places. 1.554. All right, guys, let's see how you guys can do on some of these on your own. R is this region. We found the area of this in a previous class. Go ahead and find the area of R. Area is the integral from 0 to, we need to find this intersection point. That was something that I think, I suspect some of you missed last time. So this is E, maybe we haven't done this area before. Maybe just like look like this, I'm not sure. E to the negative x squared is y1, that's gonna be the top one. And 1 minus cosine of x is y2, that's the bottom one. So we're going to do the intersection, enter. That intersection is 0.942. I remember doing that. This is 0.942. That's the intersection point. So this is going to be the integral from 0 to 0.942 of, I'm going to say y1 is e to the negative x squared. That's my top one. And y2 is 1 minus cosine of x. So it's the area of y1 minus y2. So, I didn't put integral. Math 9 is how we get to integral. The integral from 0 to 0.942 of variables y1 minus variables y2 dx. 0.591. So 0.591. That's the area. But hey, look, that was actually what the question was. I didn't actually read the question. I was just like, guys, find the area yourself. Well, great. There we go. Hopefully you found it and you got the answer to part A is 0.591. Notice this formula is going to look very similar to what some of these other volume formulas are going to look like. Now, the region R is the base of a solid. There's something, a 3D figure sticking out of the page. For this solid, each cross-section perpendicular, when you cut it perpendicular to the x-axis, is a square. find the volume of this solid. Okay, try it on your own. Let's see. Hopefully, you said that the way we're going to find it is that we need this height squared. That's the area. The area at each x is going to be this height squared. Well, what's this height? It's the top one minus the bottom one. That's how we were finding height before and finding areas. Now we're using this same height. It's top minus bottom. So it's going to be here, it's top minus bottom squared. So top minus bottom squared, because that will be the area of a square. So in this case, it's y1 minus y2 squared. That is my area, and where y1 is this and y2 is this. So the volume then is going to be the integral from 0 to 0.942. These limits will always be like the same, whether you're finding areas or volumes, of y1 minus y2 squared. And I can write this because I have written somewhere on my page what y1 and y2 are. If you have not written what y1 and y2 are, you can't do this. You have to have like explicitly written out what y1 and y2 are, and I highly recommend doing it. So guys, I'm just gonna go back up to this top one, and I'm gonna insert a parentheses. To insert something, you press second and then this INS button in a calculator. INS says insert. It's blue, so you press second first. Insert a parentheses. And then I'm gonna go to the end and put a parentheses and square it. There we go, 0.461. Okay, now, the region R, the same region, right? So whatever, looks like this, okay, is the base of a solid. Each cross-section perpendicular to the x-axis is a rectangle. A rectangle is sticking out, and it says the height of the rectangle is half the width. So the area, find the volume, guys. Hopefully you can feel good about it. The area at each x is going to be, the area of a rectangle is length times width, and the length is y1 minus y2. Okay, that's the length. That's this distance is y, like the top one is y1, the bottom one is y2. So y1 minus y2 times, well, what's the height going to be? Well, it's half the width. So 1/2, the height is going to, I guess they're calling this the width and this the height, whatever, it doesn't matter, of y1 minus y2. So half of whatever this distance was is going to be what the height is. It's like a short little rectangle. Okay. And again, since these are the same thing, we can separate this into 1/2 times y1 minus y2 squared. So this is the area at each x. And so the volume is the integral. I'm going to factor out the 1/2 to the outside because it's a constant, of y1 minus y2 squared, and it's from 0 to 0.942. And I actually already calculated this up above. So this just has the 1/2 factored out. And so I'm just going to take my answer from up above and divide it by 2. Now, guys, could you, so 0.231. Could you have, gone and set up an integral here that said, this is going to be 1/2 and it'll come out right? Of course you could have. Could you have said, could you have not simplified it and left it like this? So 0 to 0.942, oops, yikes guys. 0.942 of variables y1 minus variables y2 times 1/2 times variables. Like, you could have left it unsimplified. It's just like there's way more places to make a mistake typing it into your calculator if you do it like this. It should come out the same, but okay, it's easier to type it in the easy way, I guess. Last one. Same region, the same region R. It's the base of a solid, so we've still got that region R. The base of a solid, here's R. For this solid, each cross-section perpendicular to the x-axis is a semicircle whose diameter lies in R. So a semicircle whose diameter lies in R. Okay, well, what is the volume of this? The volume is going to be equal to, well, we need to find the area at each x. The area at each x is going to be 1/2 pi r squared. That's the formula for the area of a semicircle. And r is going to be, the radius of the semicircle is half of the diameter. The diameter is this distance. So the radius is half of y1 minus y2. And so you get 1/2, this is area, is 1/2 pi times 1/2 of y1 minus y2, that's the radius, squared. And just like before, this 1/2 will end up getting squared and we'll end up getting pi over 8. So a half times a half is a fourth, times a half is an eighth, and then pi multiplies on top. And so this is y1 minus y2 squared. So a couple ways to do it. We could say the integral of pi over 8 times y1 minus y2 squared, or we could recognize that we already found this integral and this is just a constant. And so I could take the one that we had up here, this answer, and multiply it times pi over 8. And since that's a constant, this will come out to be the right answer. Of course, I also could do, hold on, I'm just gonna take this one. I could also type in, pi over 8 squared like this, and that'll give me the same answer. I could also do, if I didn't realize, I could do, I think I said it was 1/2 pi, right? So let's see, 1/2 pi, times r squared, but r is a little bit tricky to write here. R is a 1/2 here, and we need to make sure that 1/2 is actually getting squared. So the 1/2 is getting squared as well, and that'll come out to be the same thing too. But I think if you recognize this is a semicircle and you just pull out a pi over 8 times the original area, that's nice. All right, guys, that's it for today. You'll get some practice on these volumes. Again, the idea is if we know the area, and sometimes they'll just tell you, hey, here's a formula for the area at each x, and then it's just the integral of the area. The integral of areas, adding up all these areas, gives you a volume. So whether it's semicircles and you add up a bunch of semicircles and it gives you a volume, or you add up a bunch of squares and it gives you a volume, or you add up a bunch of rectangles and it gives you a volume, all you need is a formula for the area at each x. If you can find the area of the shape at any x, then you can just do the integral of the area. All right, guys, have a good rest of your day, and we are almost done with our year, where there's not much more to learn.